Hey everybody, welcome back to the channel. Today we're going to be doing some real maths, right? Not just talking like my last two videos. Okay, so this is in fact a problem from a series of problems called Advanced Missouri State Problems. I'll leave a link to it in the description below. And it's a super cool alternated series. Okay, so let's delve into it a bit more closely. So we have 1 over 1 squared plus 1. Right, and then the sign alternates. So we have minus 1 over 2 squared plus 2 plus 1 over 3 squared plus 3. Right, and this continues forever. Okay, well, the first step, as always, is going to be to put this thing, I'm in the way, sorry, more like this. Right, to put this thing into sigma notation. And why is that helpful? Well, it's going to allow us to manipulate algebra, okay? And that's always one of our main goals, right? That's the power of algebra. What am I even talking about? That's the power of algebra, is that we can manipulate it, maybe? Who knows? Alright, so we have something over n squared plus n. Okay, but the something on the top has to be minus 1 to the power of n plus 1, and that's going to produce those alternating signs. Okay? Well, my next step, I'm just going to rewrite this slightly differently. Okay? So I'm just going to, separate this minus 1 to the n plus 1, and then I'm just going to rewrite this bottom part. I'm going to factor out an n. Okay? So now I've just rewritten it as n times n plus 1. And what does this scream to us? Right? Well, to me, it's screaming partial fractions. Right? So let's do a little side note. So we want to write 1 over n times n plus 1 as 2 partial fractions. Right? So what do we want to write it as? We want to write it as a over n plus b over n plus 1. Okay, well the next step, just times it by n plus 1 and times it by n. So we're going to get 1 is equal to, well, a times n plus 1, and then it's going to be b times this n. Right, and of course, in fact, this is an identity, so we can plug in specific values of n, which are going to help us find out the values of b and a. Okay, so when n is 0, okay, well, this is going to vanish, and then we're just going to be left with 1 times a, which is just a, of course. So, a is equal to 1. Okay, and then let's say we plug in n equals minus 1. Okay, well this is going to make this term vanish, and we're just going to be left with 1 being equal to minus b. Right? Minus b, or in other words, b is equal to minus 1. Right? So now let's take this, and let's plug it back up here. Okay, so what do we have? So this is equal to, in fact, right, this series is equal to, well, it's the infinite sum from n equals 1. Okay, we still have this part, right? But now we're going to plug in what we just found out here. So instead of writing 1 over n times n plus 1, we're going to write 1 over n minus 1 over n plus 1. Okay, so now I'm going to distribute this minus 1 to the n plus 1 to these two terms. Okay, so I have the infinite sum, n equals 1, well, let's distribute that, so I'm going to get minus 1 to the n plus 1 over n minus 1 to the n plus 1 over n plus 1. Right, and that's looking pretty good. Right, that's looking much better than this thing that we had to start with. Okay, and I notice a pattern here, right? There's n plus 1 on the bottom, and there's n plus 1 as the power here. Right? And we're dividing by n here, and we're almost raising to the power of n here. Right? We just have an extra factor of minus 1. So how about we just sort that out? And we can do that just by factoring out a minus sign. Okay, so when I factor out a minus sign, this is just going to become n, and well, this is now going to become a plus. Boom! right? Now we have the same power as the thing we're dividing by in both cases, and that reminds us of integration, right? That's something we've seen before on the channel. So how can I rewrite this? This is the piece de la résistance, right? N equals 1, and then we have the integral. Okay, well, let's first just think about what it is we're integrating. So it's x to the n minus 1, because then we're going to increase the power to get the n and divide by the new power. And in this case, we have x to the n. Okay, and of course, that's just respect to x. Okay, but that might be a bit confusing. What we have minus 1 here, we don't have x. Okay, well, that's fine. It just means we have to introduce limits. Okay, so our top limit is going to be minus 1. And our bottom limit is going to be 0, just so we don't have any extra terms. Okay, now just pause here for 1 minute. Just convince yourself that this is the exact same as this. Right? But now, how does that help? Well, this helps massively because summations and integrations can be flipped. Okay, so this is nothing but minus the integral from minus 1 to 0 of the summation to infinity, starting from n equals 1, of x to the n minus 1 plus x to the n. Right? And now how do we deal with this? Well, and in fact I should have dx, right? Because it's the integral of all this thing with respect to x. And now how do I sum this thing? Well, this is just a geometric series, right? So we can do that. So we have minus the integral of, well, what's this going to be? Okay, well, the first term is 1 here in this case, and our common difference is x. Okay, and now in this case, our first term is x, and our common difference is also x. Right, just applying the geometric series formula. Okay, in treating these as separate summations. Okay, then we have this integral with respect to x. Okay, well, the minus sign can be absorbed into the limits. Right, we can just flip the limits and absorb that minus sign. Right? And now, this is something we can tackle. Well, the first thing we have, okay, the 1 is minus 1. And therefore, the top is minus the differential of the bottom. Right, because the differential of minus x is minus 1. And as I said, right, we have minus that differential. Okay, so it's probably easier if I just write it down instead of talking too much. Okay, so I have log the modulus of 1 minus x. And of course we have our limits as 0 and minus 1. And again, this expression comes from just the integral of this first part. Right, now let's tackle this. Okay, so we have plus the integral from minus 1 to 0 of x over 1 minus x. dx, right? Okay, so this first thing, log 1 is nothing, and then we're going to have log 2, okay? And it doesn't matter about the modular sign because log 2 is obviously positive. So log 2 plus this thing. Okay, well, let's make a substitution. So I'm just going to write log 2 plus the integral, okay? We can't bother to rewrite it. So let's go ahead and use a substitution. Okay, let's do that over here. Right, so what can we do? Well, this thing on the bottom is the problem. So let's sort that out. Let's say let u equal 1 minus x. Right, and then minus u is going to equal x minus 1. Okay? And then 1 minus u is going to equal x, okay, which is the thing we have in the numerator exactly as we want. So let's plug that in. Okay, so now we're going to have the integral. And we're entering the u world, so I'm going to use my red pen. So our limits. Now when x is 0, u is 1. When x is minus 1, we have 1 minus minus 1, which is 2. Okay, now let's plug in our substitution. So we said x is nothing but 1 minus u, and 1 minus x was u itself. Okay, and then of course dx is going to be minus du because it's a linear substitution where we've just introduced a minus sign. Okay, so this is going to be minus du. Okay, again, let's absorb that minus sign into the limit so it looks a bit prettier. So we have 2 on the top, and we have 1 on the bottom. Right, and now, what can we do? Well, we can split this into 2 separate parts. Okay, so we have 1 over u, right, and then we have minus u over u. It was minus u over u, but u over u is just 1. Okay, so that is the final integral we are left with. And now let's just do the final steps. That's going to be log 2. The integral of 1 over u is of course log u, so we're going to have plus log u, and the integral of minus 1 is minus u. Right. And then when we plug in our limits, okay, we're going to get log 2, and then we're going to get minus 1 when you plug in the limits, right? I'm not going to write it down because I have space. So altogether we are left with 2 log 2 minus 1. Right? Super awesome problem. And it all comes from that integral, right? And the fact that we can switch it. It's such a cool trick. When that works, it is super satisfying. Okay, so that's the end of the problem. I hope you enjoyed. Yeah. Leave me your comments. We're almost at 100 subs, which is super exciting for me. I'd like to say thank you if you've supported the channel, left comments in the past, and I'll see you guys next time.